Thank you very much. Good morning, everybody. My name is Jason Maude, and I am the Head of Technology Advocacy at Starling Bank. Who here has heard of Starling Bank? Good. That number keeps going up and up every time I speak, which is good. I'll introduce Starling Bank in a minute, but what I want to talk to you about today is continuous delivery and how you do that at a bank. The problem with banking is that it's very conservative, as was just mentioned. It's an industry which prides itself on being slow, cautious, on having trust given to it from its customers. So, the banking industry might be seen to be fairly immune from all of the brilliant changes in software and all of the things such as continuous delivery and DevOps and so on that have come about in the past decade or so. Who here works in banking or financial services of some sort? Yep, that's a typical London audience. There's a lot of financial technology, a lot of software going on here. And if you're like me, and I've been working in London since I left university and working in financial software since I left university, you'll probably have found that there is a lot of resistance to these newfangled things that these new upstart companies like Amazon and so on, and Google and all of these big tech giants are doing. You know, these whippersnappers come around and they don't know what they're doing really. They've only been going for a few decades. We're a bank. We've been here for hundreds of years. We know what we're doing and we do things the right way, which is very slow, very deliberate. So when banks see things like this, they balk. This is a quote from Mark Zuckerberg, which was, for a time, used as the unofficial motto of Facebook. I believe they adopted a more corporatist slogan later on. But for a time, this was the motto of Facebook: move fast and break things. Unless you are breaking stuff, you are not moving fast enough. Now, the point of this quote was not that you should introduce bugs deliberately or not care about the quality of the code that you're shipping. The point of this quote was about priorities. And the priority was that you had to get code in front of the customer. If you weren't getting code in front of the customer, you weren't really learning what that code was doing. You could, in your sort of disinfected, isolated environment, you could create as much code as you liked. But unless you actually put that software in front of an actual user, you weren't actually learning what that code was doing. So this idea of sometimes you have to sacrifice 100% quality and introduce something which is a bug or a feature, into the code in order to get it out faster became an accepted norm in the tech world. And a lot of this sort of fast, continuous improvement, continuous delivery, get a minimum viable product out there and then iterate over it and over it and over it, became the norm for the tech world. And this is where, the sort of continuous delivery idea came from. But banks didn't like that. This quote from Harry Potter, which symbolizes, I think, the idea of banks, the idea that banks want to project. This bank is the safest place in the world. Now, why do banks want to do that? Well, the biggest asset that any bank has is not, in fact, money. It is, in fact, trust. The trust of consumers. The trust of the people who have deposited money in the bank. No bank holds enough money to pay back all its depositors at once. So if all of the depositors go and simultaneously try and withdraw their money, that is called a run on the bank, and the bank generally collapses. The most recent example of that, in the UK at least, was Northern Rock. If any of you remember the scenes of people queuing up outside Northern Rock branches to try and withdraw their money. they they really wanted to get their money out because they didn't trust the bank anymore. They didn't trust that Northern Rock was able to keep itself liquid. So trust is the greatest commodity a bank can have, and they want their consumers to trust that the bank is reliable and that the bank is secure, that they will be able to get access to their money, and that the money will be handled in a secure and appropriate manner by the bank. And this leads to an inherent conservatism within the banking industry, and that conservatism leaks into its IT, right? The IT departments adopted this conservatism. Releases in traditional incumbent banks were done once every 3 months, if that. And even that was seen as a bit too, whoa, slow down, cowboy. You're going a bit too fast here. So this inherent conservatism that banks had went into its IT. Its IT decided to release things very slowly, very gradually, very deliberately, citing, the need for reliability or security or frequently regulation as the things that prevented them from going fast. But at least that sort of, insistence on reliability and security and going slow and being conservative meant that banks never suffered IT failures. Obviously, this wasn't the case. Banks were suffering IT failures all the time. One of the most famous ones that happened back in 2012 was when a well-known high street bank, whose name has been redacted to protect the innocent and the guilty, decided to do a release of code to change something called a batch job scheduler. This is a thing that basically a piece of code that sits and runs at the end of every day to schedule tasks that need to be done at the end of the day and to kick them all off. And so the release was performed, but before the release was performed, everything was put in place. The team made sure that the code had been tested. Sign-off was achieved from all of the 5 or 6 different executives from whom sign-off was necessary. A rollback plan was put in place just in case something went wrong. And all of this was done, and everyone was thinking, yep, we're good to go. They pressed the button, they did the release. And they looked at overnight, they looked at some of the performance figures, so they had monitoring in place as well to make sure that the release was going okay. And they said, yeah, the monitoring, it doesn't look right. We're seeing some significant slowdowns in particular processes. We think we need to roll back. And so they initiated their rollback plan, well-documented, well-recorded rollback plan. And at that point, all hell broke loose. Because it turns out that this rollback plan, while it successfully rolled back the code, didn't roll back the database migrations or the schema changes that had been made. So the code was running at one version and the database was running at a completely different version. And this meant that when the batch job scheduler ran the next night, it started doing crazy things. It kicked off a job and the job failed. And then it went, oh, okay, I don't care, I'll kick off the next job. But it turned out that the second job required the first job to have completed successfully in order for it to run successfully. And the batch job scheduler didn't care that it was causing chaos. It was just merrily running jobs all over the place, causing figures to get completely out of line. People's mortgages were miscalculated. Their balances were completely out of line. The bank had to shut down internet banking for almost a month from some customers. One of their subsidiaries, the batch job scheduler took so long because everything was wrong that the next night's batch jobs started up while the previous nights were still running, which caused even more chaos. So this, complete disaster was just ruined everyone's day, everyone's month. and there were a lot of unhappy customers. And you can see what that sort of thing would do for trust. If you're not calculating what payments have to be made correctly, and you're not calculating what people's balances are correctly, that can ruin trust. And trust is the biggest asset for a bank. So you could adopt the Facebook Mark Zuckerberg model of development, developing fast and breaking things, or you could adopt the traditional incumbent bank model of development, developing slow and breaking things. Either way, if you develop, you break things. Once you accept that you are going to break things, and crucially, once you take that and put it into your code, then you can start developing in such a way that provides both the reliability and security that you need as a bank and allows you to develop and deploy in a continual or a continue-ish manner. So, before I go on to explain how Starling Bank has done that, I would just like to introduce briefly who Starling Bank are for those of you who haven't heard of us. So, Starling Bank is a mobile-only bank. We're one of what are called the challenger banks, the banks that has sprung up in the last few years. So we like to think of ourselves as a tech startup or a tech company now with a banking license. We are a cloud-based, mobile-only, for the moment at least, bank. So you get the access to the bank account by downloading the Starling app onto your phone and logging in, providing all of your identification details and so on through the mobile, and then doing all your banking through the mobile. And we provide all of the stuff that you would traditionally expect from a bank, such as a debit card, direct debits, faster payments to other banks. We also provide features that are fairly new, innovative. Not many other banks have them. Things like aggregated spending data or fine-grained granular card control, the ability to switch your card off for ATMs but leave it on for online purchases or contactless payments, for example. And we built this bank in a year and a half, really. A year is a bit of an exaggeration, but we started building the bank round about late 2015, early 2016. That's when we started writing the code for the bank. We launched 2 years ago last week on May the 9th, 2017. And that's when we publicly launched the bank into the App Store and allowed members of the public to sign up for the bank. And in March 2018, we were declared the best bank at the British Bank Awards, a feat which we repeated in March 2019, so we're the best bank 2 years running. The question here is, so how did we manage to do that? How did we manage to start from not having a bank to launching a bank, and then 10 months after that, becoming the best British bank? How did we manage to do that while still maintaining this reliability and security? How did we manage to develop fast, break things, but make sure that we broke things in a reliable manner? So, building reliable architecture. The first question that I want to ask with this architecture is, why don't we just create a monolith? So before I quickly dismiss the monolith as, oh, no one uses monoliths anymore, let's question why not? Why don't people use monoliths? Well, we didn't want to use a monolith because it's not reliable. If something goes wrong in your monolith, and as we've discussed previously, if you develop, things will definitely go wrong, then you can't degrade gracefully. Your monolith is either on or it's off. It's either there or it's not. If you have a distributed system with lots of different portions, lots of different parts, then parts of the system can degrade, but you still have other parts there and available. The monolith doesn't degrade gracefully. It's also not scalable, and there are other, various other problems with it in terms of development. But the main problem for us, not reliable enough. So we dismissed the idea of a monolith fairly quickly and moved on to a more distributed architecture, one with more more parts that we can control independently of each other. Now, if you're in a distributed architecture, the next problem you've got to avoid is the problem that we saw earlier with our batch job scheduler. And that is, if you've got a distributed architecture and you want it to be reliable, you have to cope with the idea that if there is a bug, a problem, a fault, bad data in one element of the architecture, that can quickly spread to another one, and then another one, and then another one. You can spread a problem like a virus, especially if the system just picks up an idea, picks up a command and says, oh, this must be fine, run it on, segment A, system A says, system B, run this for me. And system B blindly says, yeah, sure, I'll run that for you. That's okay, that must be fine. And then runs it. And then system C says, oh, I've been asked by system B to do this. Oh, it must be fine, I'll run it. And as we saw with the batch job scheduler, if there are implicit ideas that, in order for the second part of a command to work, the first part of the command must have succeeded. If that's not true and you haven't checked that, then you can get into a state where one part of a command gets completed but another part doesn't, and then you get into a unholy mess, which it takes a long time to sort out. So we operate at Starling on something that we call self-contained systems. And self-contained systems are, we've adopted this architecture. You can go and read more about it at that website. We haven't fully adopted all of the principles of self-contained systems, but we have taken a lot of the ideas from it. Now, the main ideas that we've taken are that we have self-contained systems, which we don't really call microservices. They're more, I like to call them microliths. They are essentially services which perform functions in one business area, such as card processing or faster payments processing or direct debit processing, something like that. They have they do multiple different things, but they're all in one area. All of these services have their own database, their own logic, their own APIs, which connect to various bits of the outside world. Startup of one is not dependent on startup of any of the others, so you can run each system completely independently of all of the others. There's no, they also have their own transactionality, so there's no distributed transactions. You don't have a transaction that either rollbacks or commits across multiple systems. And all of this is fairly important to remember for later. So, here's a vague network diagram, a vague architectural diagram. So these purple boxes represent our self-contained systems. They're running in the cloud. We probably run 2 or 3 of instances of each service at any one time. And that's to make sure that we have, not only a distribution of the workload that we need to, but we also have redundancy in case one system goes wrong. We can always fall back to a second system. But we can scale up the number of services that we, instances of any particular services that we run in order to cope with increased load in one particular part of the system, for example. These services can be contacted by each other through their API, or by the mobile app, or by the management portal app, which is our browser-based system used by the bank managers to run the bank. They might also be contacted by various outside agencies. For example, the card processing service will be contacted via our card processing provider, for example. So, in order to make sure that we are processing instructions from the customer or from the bank managers or from the outside agencies in a reliable manner, we need to have some principles in place which will allow us to do this. And we came up with a few architectural principles and then gave those a name, which was this. It just rolls off the tongue, lo sciaditio, which stands for lots of autonomous services continually trying to do idempotent things to each other. Very memorable, very simple. Then we presented this to Adrian Cockcroft at Amazon, and he said, well, why not just shorten it to ditto architecture? So we said, yeah, that's much more memorable. So we shortened it down to ditto architecture, which stands for do idempotent things to each other. To others, rather. So what are the principles behind ditto architecture? Well, here are the most important ones. First and foremost, ditto architecture means that any command issued by a consumer, customer of the bank, or a bank manager, or an outside agency that's giving you instructions must be completed at least once and at most once. Now, why didn't I just say once there? Well, saying at least once and at most once gives you the two failure modes that you must try and counteract. Everything has to be done at least once. You don't want to say, you know, a customer to go, I'd like to make this payment, please, and for you to just go, sure, I'll do that, and then not do it. That's bad. You also don't want the customer to say, I'd like to make a payment, please, and then say, sure, how much? And they say £20, and you go, okay, I've sent £40, thanks. You know, because that's also bad. You have to, in order to make sure that you are reliable, in order to make sure you maintain this trust, you have to do everything at least once and at most once. You have to work towards correctness, towards eventual consistency. Now, this is the no distributed transactions thing. Because you have no distributed transactions, and because an individual command might require changes in multiple services, you have to cope with the fact that at any point along the way, something could fail. At any step along the way, something could go wrong, and you have to be able to cope with that. You have to be able to catch up what you're doing such that eventual consistency is achieved. So if something fails halfway through, you have to be able to start again and make sure you don't repeat the first bit of what you've done, but that you do the last 2 or 3, however many stages. So this at least once and at most once principle not only applies to the command as a whole, it also applies to each individual section of the command that is being run in these different services. We keep the smarts in the services rather than in the pipes. There's nothing in the pipes between the services that are contacting each other. It's simply a REST endpoint that you call, and any queuing of work or any events that need to be driven are kept in the services themselves. Rather, there's no piping, clever piping system between the services. And overlying this is the general idea that the services shouldn't trust each other. Go back to that batch job scheduler. The main problem it had was that it trusted the services it was calling. It made the call out to them and said, oh, well, I've made the call out to them. It must be fine. I trust that they will have done what they need to do. No, don't trust. The services should be mistrustful of each other, mistrustful of instructions coming from outside, both in terms of reliability and in terms of security. I'm not talking much about security in this presentation, but that's also another big thing, that the services should be mistrustful in a security manner of each other. Okay, I'm going to talk through an example of how this works now. So the example I'm going to talk about is making a payment. Okay. So this making of a payment, the customer goes into their app and says, I'd like to send £20, please, to this bank account, go. Now, the first thing that does is that gets sent via the mobile phone through a REST endpoint to the customer service. And the customer service stores information about the customer's balance and also about which payments they would like to make. So, some brief initial checking is done, the minimum that can possibly be gotten away with, mainly to check that the customer has enough money to do this. And once the customer service has checked that, it says, I've checked that, it's all fine, I will save the fact that this payment needs to be made and respond with, okay, 201, okay, everything's fine, I've done that for you. And that's the only synchronous bit of this transaction. Next up, customer contacts payment and it says, hey, payment, I'd like you to make this payment, please. Now, payment is the service that actually encodes the message and sends it out to the faster payment network to say, hey, faster payment network, please make this payment to this other bank account. And customer will contact the payment system and say, please make this payment, and payment will go and take that instruction, save it in the database, and then respond, thank you very much, okay, done. It won't have done anything, it'll just say, I have acknowledged your request. Payment will then send out that message to the faster payment network, and then it will have to contact bank. Now, bank is where the ledger is stored, the service where the ledger is stored. And we need to record the fact that this money has been paid out to the faster payment network, because at the end of the day, they'll come and want to settle up with us for our net ingoings and outgoings. So we need to put this in the ledger so that we can settle the right amount of money with them. And so payment will say to bank, hey, bank, please save this payment in the ledger. And bank will go, thank you very much. Yes, acknowledged. It will save a record that this needs to be put in the ledger, and then it will put it in the ledger in its own time. All very asynchronous. Now, that's all very nice, happy path, brilliant, who cares? What we really care about is what happens when things go wrong. So, let's imagine that customer gets contacted to make a payment, saves validates the payment, saves it in its database and says, right, I'm ready to go. Then it contacts payment and it says, payment, please make this payment. And payment doesn't respond. There's no acknowledgement. So, customer needs to make sure that it does everything at least once. It's contacted payment and payment hasn't responded. So it does not trust that payment has done what it asked it to do. No, it says, well, it didn't respond. So obviously something went wrong. So, sometime later, a little bit of time later, it retries. It says, hey, payment, please make this payment. And this time payment responds and says, I have made this, acknowledged, thank you very much, I will do that. And customer goes, right, now I'm done. I've received a successful response back. So this is the retry concept, which provides that concept of doing everything at least once. Now let's imagine the payment contacts bank and says, hey, bank, put this in the ledger, please. And bank responds, bank does that, puts it in the ledger, responds, but the response gets lost. Or the payment server gets switched off, the instance disappears before bank can provide that response. So, obviously, payment hasn't got a response, so it thinks, well, I haven't got a response, so I'm going to try again. It tries again. Now, this is where the idempotency comes in. Idempotency, in this context at least, is the idea that if you ask if you make a request twice, it has the same effect as if you made the request once, or if you made the request 3 times or 4 times. Now, the way that idempotency is achieved is you might have noticed that I've put UID over all of the things. So every command has a UID associated with it. Every payment, every card transaction, every address, every person, etc., has a UID associated with it. And that UID follows it throughout the system, follows it throughout all of the different services. So if we try and make a payment into the ledger, we are going to use the payment UID as the unique identifier to indicate in the ledger as well. So we come to the ledger and we try and put it in a second time, and bank goes, no, I've already done that. I've already got that. So it doesn't complain. It doesn't throw throw an error or an exception and say, oh, there's a problem here. You're trying to do the same thing twice. It just goes, okay, thanks very much. I will take that, and I will, I've done that already. Fine, what you want has been achieved, payment. I've done that. Thank you very much. So with this retry and this idempotency, we can achieve the at least once and at most once ideals that we are looking for. We do this with a device we called the queue manager. So we have implemented a common queue architecture across all of our different services, which will essentially look in the database for items that have been queued up, pick them up and farm them out to different workers who are running the QIE queue item executor associated with a particular command. So when payment needs to send to bank the particular item, the queue manager will reach into the database, pick out the next item, farm it out to a queue item executor. If the queue item executor comes back and goes, it's all successful, then the queue manager will go, great, I'll mark that one as done then and forget about it, or put it in the done pile. However, if the queue item executor returns and says there was a problem, the queue manager will put will basically add a delta to the timestamp of when it should next be processed. And it does that in an exponential back-off fashion. So it'll, try quite a lot in the first second, and then it'll gradually get more and more, if it gets repeated failures, it'll gradually taper off until, it's only trying once every half hour or so. Okay, great. So we've put this in place. So now let's come back to our initial question. How does this allow us to, we've got this reliability, this safety, this distrust built into the code itself. What benefits does that give us? Well, first of all, instance termination is safe. This I suppose is the big benefit. What that means is that I can come along at any time and switch off an instance of a particular service. And even if it was halfway through processing some things, I don't care, because I know that everything will catch up to be eventually consistent. So I can just go along and kill something, throw it away, and then another instance will come along, be spun up, and it will start picking up the work again from the database, farming it out to its executors and so on to execute in an idempotent manner, and everything will catch up to where it needs to be. Things might take slightly longer, rather than being, milliseconds, they might take seconds or minutes, but that's fine. Generally speaking, we're not operating in an environment here where everything needs to happen within milliseconds or microseconds. Consumers are generally fine if a payment takes 5 minutes to get from one place to another. I say generally fine, they were fine previously. We might be changing expectations of that. I heard someone the other day when I said that complain and say, no, they're not, they want it within seconds now. Hopefully we haven't changed expectations that much. So, what does being happy with just terminating instances give us? Well, the main one is that we can have this continuous-ish delivery of the back end. So we deliver to our back end to production once or twice a day, generally speaking. So gone are the days where, you're backend server code would go once every 3 months. We do it once every day. There will be a release every day. We get nervous if we build up more than a day's worth of code because we like to know exactly what's going out in the release. So we try and release every day. We can generally get a release out in about, in under an hour's time, and that includes all of the sign-off that we still need to get because we are still, a regulated, licensed bank, so we still need to get the sign-off and the auditability trail and all of that sort of thing. But we can get it into production fairly quickly. And this allows us to develop at a rapid pace and deploy new features and bug fixes at a rapid pace. We have used Slack to automate our releases, so we can, use Slack to develop our own audit trail. So Slack will our chat ops bot called Roller will sit there and say, "Hey, I'm releasing this particular version to production. Here are all the commits that are going out." And then it will, once it's happy with that, it will stage the release for us and then ask for approval automatically. And that approval can then be given by people with the appropriate permissions, and who has given approval is then logged in Slack, and then the release can be performed via the AWS console. We also have to inform everyone that we are doing a release. And the way we've chosen to do that is by posting in Slack what we call the rolling GIF. So this uses Giphy to find a GIF that indicates rolling of some manner, and we post that to indicate, hey, we're doing a roll here. We're rolling the version. Now, this is part of an audited process, so the auditors have to come in and look at this and sign it off. And they have come in and looked at it, and as with everything we do, they went, "What?" But then eventually they were like, "Well, you're doing what you're supposed to be doing. You are informing everyone that a release is going out. You're not hiding anything. Anyone can go and look at this audit log of what is going out and check it. So this is good." And we found this a lot with the regulators, that we've done things that other banks and financial institutions say, "Well, no, that's impossible." No, they sit there and go, "No, well, alas, we would love to delight our customers, but alas, regulation prevents us from doing so. We're so sorry." And we're like, we have shown, no, that's not the case. You can follow regulations. You can provide all of the auditability that's needed. You can do everything that's needed to work in one of the most regulated environments in software and still release at speed. And if something goes wrong, we have graphs everywhere. We have monitoring everywhere. We have all of the things we need to make sure that we are doing what we need to be doing and that things are running correctly and that we haven't broken anything. We have both the visual graphs up on the wall, and we also have, if something goes really wrong, then we have alerts that will automatically call up the on-call engineer and say this metric is out of line, we're doing something wrong. We can test killing apps, again, via Slack. We can just tell it, hey, kill this particular server in demo, and it'll take that server down. We can go, ooh, what happened when we took that server down? That was interesting. Fantastic. So we can test it. Now, testing in demo is all right, but it doesn't really show you what happens when things go wrong. So we also like to kill servers at random in production. So we have a very small simian army. It's not really an army, it's one soldier, who goes round and will, at random, terminate servers using the chaos engineering concept. And, you know, this is very small potatoes to when you compare it to someone like Netflix, obviously. But when you compare it to other banks, I say this and they go, you're mad. You're just killing servers and instances in production. What are you doing? But this is the only way that we can prove to ourselves that our architectural concepts really work and that we really are deserving of the trust that our customers place in us. So let me end with some important takeaways from this. Firstly, mistrust. Design your software to be skeptical. I've mentioned trust a lot in this presentation because it's very important for banks. If your customers are going to have trust in you, and if you are going to have trust in your software, you need to make sure that your software doesn't trust itself. That individual services, individual points within your software architecture are mistrustful of others and will check and say, whoa, you're asking me to do this, have I already done it? You're asking me to do this, do you have permission to ask me to do this? You're asking me to do this, you know, did I get a good response? I asked someone else to do this, did I get a response? Or did I just, you know, not hear back from them that they had done a thing? So design your software to be skeptical, mistrustful. Give everything a UID, scatter UIDs everywhere. They don't run out, theoretically. So scatter your UIDs everywhere, make sure everything has a UID because that's how you ensure that you're doing things in an idempotent manner, that you're only processing things once, even if you're asked to do them 2 or 3 times. Fire alarms are good, alerts are good, have them. Again, that's another way that you can guarantee that trust. You know, you can trust your software if you're constantly monitoring it and saying, are you doing what you're supposed to be doing? There's a whole other talk on, you know, you can give on what type of fire alarms you should put in when, you know, what things you should call up the on-call engineer at 2 in the morning for. It shouldn't be everything because then people switch their phones off and so on. But in general, having alerts and monitoring is a good thing. And finally, if you put everything, all of this together, you can do anything that you can undo. So if you make a mistake, if you put something out like that mystery batch job scheduler, if you've got everything designed to work in a reliable manner, in a secure manner, if that's baked into your software, then if something goes wrong, rather than going, quick, where's the rollback procedure that we never use? Let's hope it works. You can just go, that's fine, we'll fix forward. We'll just create another fix, spend an hour building the fix, checking it, testing it, then release it into production, and everything will catch up to be eventually consistent. And at most, we will be out for an hour, not a month. If you do all that, then you can have a system that is reliable, secure, and you can deploy fast at the same time. Thank you very much.